Alright, well, I just found out that you can operate a smartphone with latex gloves on. Um, I wanted to talk about tachometers. Okay, optical tachometers like this one here. This is a high dollar unit that I bought a long time ago that has controls to adjust its speed, and you get a digital readout, of, like, for example, the RPM of a motor. Now, do you see what's going on there? There's a white square on that, and it looks like it's standing still, um, because the frequency here matches the frequency that is rotating. And I'll turn this motor off here. This thing it actually decelerates. This is out of a floppy, 5.25-inch floppy disk. So it was real simple to get it to work. You just had to, hook it up to 12 volts essentially, with the red and the black wire, and the yellow one controls the LED, and and the blue one, is what slows it down. I'm wearing gloves, by the way, because I'm messing around with batteries. And the acid coming out of it, as you can see. But at any rate, the point is you can see I got one little sticker on it, and also got a C printed on there, but I thought a sticker would be a little easier to visualize. So, but again, it's completely stationary because of the fact the frequencies match. Now, let's say I didn't have the frequency figured out yet. So, let's say I started at a much higher frequency, because it's actually better to start, if you've got a tachometer in with a frequency readout like this, it's better to start with a high frequency, and I'll show you why. Okay, let me start. Slow it down. Okay. Now, what you do is you just slow it down until it looks like everything's stopped. Okay, and since we are seeing 4 squares, that means we have 4 times the frequency that it actually is. So, 1145, if you divide that by 4, you're going to come up with, pretty much the 284 or 5 that it was set at. So, because that sounds about right. So, now if you cut the frequency, okay, you see what we got there? You can take time to tune these in, but this is approximately right. It does have a fine adjustment on it. Okay, so now we're seeing 3 of them at 855. And if you're seeing 2 of them, which approximately are here, we're at 572, which, is 280 times 2, or 285 times 2. So, at any rate, but that's how you use it, though, is that, if you're over the frequency, you can count them like this and know how much over you are. So you really only have to just get it to stand still in time like this once, and count how many of your reflections you're seeing, and then just divide that by the frequency readout. Because if you go below the frequency, like we know it was 280, so, you will find other frequencies where it looks like it's standing still too, but in fact, it'll actually be too dim. In fact, you can see it how it, you see two of them, but they're alternating. So, and that's at 192 hertz. So, the point is that, you'll see other frequencies where they appear to stand still, but, the point is that you're not getting the right reading. Because, if this was faster, like 5,000 RPM, well, there'd probably be something at 4,500 RPM, etc., and you wouldn't be able to see them alternate like I'm seeing right now. But that's why it's better if you're going to, try to use a tachometer, just try to go to a speed, which should be in the ballpark, if not faster than you think, and then count the number of squares. So, it's just hard to do it at faster speeds, but you can see that we're getting to the point where we're counting, like 7 of them, so that suggests 7 times the frequency. So approximately, and here's 6 of them, so we're about 6 times the frequency. But that makes it a lot easier, to actually check this. Now, you may say to yourself, well, who cares? I don't have, one of these expensive lights. I mean, I know I paid a few $100 for this like 20 years ago. But the thing is that, if you wanted to, you could make, I would say, you might be able to check a motor like this, but you can't because you can't count the number of objects. So you actually need something that's visible from, like the top of it, looking down at the axis. So, if you want to actually be able to measure that like that. So, but yeah, that's, it works in a situation like this, but this wouldn't work, even though you can certainly see a lot of frequencies where it stands still. It's just, you're not going to be able to measure with just one of these because, you won't be able to count them, so you won't know if you're over or not. But at any rate, the point I was going to make is that, when it comes to like LED, you can make your own strobe light if you have like an Arduino or something like that. You can actually use high-powered LEDs just as good as you can make one of these, and you could have a little readout on your Arduino display, telling you how many times it's flashing, and do the exact same thing. You just have to get some of those hell, LED strips like that would probably work. You just have to, I don't know if you can see them on the camera here. Probably can't. Yeah, like that. It would probably work. You can just take some of those light strips and because LEDs can switch on and off really, really fast, probably even faster than a xenon bulb, believe it or not. So, in fact, I discovered that back in my sign days when I was making, graphic displays and, which were strobed, and man, you could see, like table fans, in the room with all the lights on, they would look like they were standing still. But yet they were on. So, it was kind of an interesting observation. But at any rate, yeah, you should be able to, do the same thing with an Arduino. Take a couple of buttons, put a power transistor in there and have it, switch to this 12-volt strip or whatever back and forth, a foot of it or whatever it takes, however bright you want it. And, and have a readout on the thing and have a couple of buttons so you can increase or decrease the frequency. And, you can make your own strobe light that way, and it wouldn't be difficult. So, anyway, that's an option, is what I'm trying to say. But you can do the same thing. And I was going to say, too, that, strobe lights like this, are much better to have. There are other techniques you could use to to measure the frequency or the RPM rate of a motor. One involved using Audacity and putting a little flag so it beat against a book of matches. As it turned, creating a frequency, and you just record it on your computer and used Audacity to see, to count the frequency, and and then do a little math on it, and you got the RPMs. Okay, that works, and there are ways you could probably hook this up to an oscilloscope, like that, and and look at the the commutator spikes, because there are commutators in here, two of them. But every so many times per revolution, it's going to make and break contacts that creates noise. That should be observable as a periodic pattern on an oscilloscope. The problem is you do need to know how many coils you have in these motors. So you're probably going to have at least three, but who knows? I mean, there could be motors with 7 or 9 or whatever. It'll always be an odd number. I would imagine. Um, but the point is that that really wouldn't work as well as as a tachometer, where you got the ability to see these things. But another cool thing, I mean, they call tachometers the mechanical engineer's oscilloscope, because, for example, let's say you were working on helicopters, okay? Well, you could tune this frequency in and not only find out how fast the blades are turning, but you could actually watch the blades tilt, as you adjust the controls in the helicopter. So you can see if a mechanism is working right even when it's running at high speed. And that's why tachometers have more uses than just trying to measure motor RPM. And given the fact you can make a simple one with an Arduino and some high-powered LEDs, I mean, that could be useful for more than just checking your motor RPM, is the point I'm trying to make. So anyway,